Okay, guys, how are you today? Join me in welcoming Amir, who is a final year PhD student at Max Planck. His research interests lie at the intersection of causal inference, explainable machine learning, and program synthesis. He's here with us today to talk about human-machine collaboration, more precisely towards trustworthy human-machine collaboration. Thanks for coming, Amir. The floor is yours. Thank you.
Perfect. Well, can you hear me in the back? Okay, good. Thanks for everyone who's good to that you guys are also hearing. All right, well, thanks for giving me your time, and I'm happy that you have something to munch on while you listen. My name is Amir, and as Mohammed said, I'll be talking about this research agenda called Towards Trustworthy Human-Machine Collaboration. I'll start the talk with a brief career review, just so you get a sense of where I'm coming from, and then I'll talk about what this means and the different angles it has. So I consider myself a scientist, an engineer, and an entrepreneur. I started my bachelor's in 2010. And what this means is that I like working on difficult problems, engineering and actually building a solution, and also delivering value to a real world problem. Throughout my career, I've had the pleasure of putting on different hats, starting as an engineering science at the University of Toronto, arguably one of the most elite engineering programs in Canada. I had the chance to not only build technical systems, but also social systems. I participated in various leadership clubs and earned certificates thereof, did a year-long internship at BlackBerry, co-founded a couple of startups with friends in Toronto. And for my contributions to the engineering science community, I was awarded the Spirit of EngSci Award in 2015. Upon graduation, I joined Facebook as a software engineer, where I came to appreciate what it means to build systems in the service of billions of people. My colleagues at Facebook New York, specifically those at Facebook AI Research, inspired me to go back to school. And so I went back to Canada, this time taking up computer science at the University of Waterloo. There, my thesis focused on nonlinear random projections. For those of you who were in the lecture yesterday, you heard about the linear form of random projections. For those contributions, as well as some parallel AI startup consulting, I was awarded the Alumni Gold Medal Award, an award that's given once per year to a master's student, and also consequently sponsored by NSERC as well as CLS to pursue my PhD in Germany and Switzerland. Here, not only did I explore the fascinating area of research on causality and explainable AI, which we'll hear about more today, but I also fell in love with writing, because writing is an important means of proper knowledge dissemination. And for contributions in my PhD, as well as mentoring and all this, I was awarded the Google PhD Fellowship in Machine Learning and got to spend some time at Google Brain and DeepMind. There's also some other works that I'd be happy to chat about later, including Prince of AI, where our mission is to educate the world on AI, the public. Okay, so let's talk about the research agenda. And we see this figure here. So the advancements in technologies such as the keyboard, mouse, touchscreens, voice-enabled interfaces, and now data-enabled interfaces such as ChatGPT have delivered a lot of magical experiences over the year. However, despite these magical experiences, many questions remain open. Specifically, one would ask, how does one recover from or overturn poor experiences via decisions made by AI? 2, how does one assay the safety, factuality, and ethics of AI systems to foster trust in AI? And 3, how does one design systems that make use of the best of both human and machine abilities? In my research agenda, I argue that to answer these questions, the next logical step and the solution to all of this is to facilitate even more interaction, discussion, and communication between humans and machines, of course, within certain guidelines, with the agenda titled Towards Trustworthy Human-Machine Collaboration. I'm going to first spend 20 minutes roughly talking about how my PhD has tackled the first question, and then talk about some future work. Okay. So my PhD work was on the topic of algorithmic recourse, and this the next few slides is a summary of work done with colleagues from across Europe. Okay, so this is, let's consider a case study. This is Edward. He's 28. He has a salary of $75,000, a bank balance of $25,000. He's employed as a software engineer, and he's single. Edward is looking to buy a home, and after months of scrupulous savings and many open house viewings, he's finally found one that he's fell in love with. But in order to buy the home, he must first visit the bank. Now, the bank may use a system such as this one to decide whether or not Edward gets a loan, or perhaps one like this, or one like this. And typically, as the model becomes more complex, it's better able to detect patterns and nuances in the historical data set. However, it sacrifices something very important, which is its understandability or interpretability. Before we define what that is, let's look at some other stakeholders that exist within this setting, including the model deployer, such as the bank, which may ask, what are the most influential features towards this decision? Or they may say, a regulator or a governing body may say, is the system acting fair by relying on sensitive attributes such as age and marital status? And individuals such as Edward, who didn't get the loan, may ask, well, I didn't get it, why not? And what should I do the next time I apply? All of this falls under the umbrella of the field of interpretable machine learning, or XAI, explainable AI, which is defined as the ability to explain or to present in understandable terms to a human. XAI has two broad goals, being one, to understand a particular decision by a system, and two, to recommend actions that would result in a desired output. A recent method that has been used broadly to attempt to answer these questions is called counterfactual explanations, statements such as how the world would have had to be different for a desired outcome to occur. For example, if your salary had been 100,000 instead of 75, you would have been offered the loan. Now, let's see whether or not counterfactual explanations, or CFEs, actually satisfy the goals of XAI. So let's once again consider Edward. He's at time t0 when he's rejected. Edward's characteristics or features are gathered together and represented in the feature vector xf, representing x factual, and y here is rejected. So let's assume it's a 0 label. If we look back in time, at time t0 minus t, there exists a hypothetical Edward such that if his feature vector took on the values of x CFE, he would have been offered the loan. This is called retrodiction. If we use the same logic and project forward in time, assuming the world is stationary, the classifier remains the same, then the same feature vector, xCFE, at time t0 plus t, would also be offered the loan. However, something is missing from this photo. And in layman's terms, this diagram tells Edward where he needs to be, but not how to get there. And so we recall one of the primary purposes of explanations is as a means to act rather than merely understand. And so the missing link in this diagram is the link there, which corresponds to something called algorithmic recourse, or recourse based on algorithms. And that is the actions required for, or the systematic process of reversing unfavorable decisions made by algorithms across a range of counterfactual scenarios. Okay, so in this work, what we want to do is we want to show that existing work falls short of actually giving us an actionable recommendation, and then see how we can generate those recommendations in general settings. So let's once again look at Edward. He's now standing on a red dot because he's rejected. And let's assume that the bank is using a linear decision boundary here, represented by h theta. So the original counterfactual explanation problem in 2017 was formulated by Wachter et al., which focused on this optimization problem here. Basically, it's saying, find me the nearest hypothetical individuals on the other side of the decision boundary. This optimization problem was then reformulated a couple years later, almost the same thing, but now instead of focusing on finding the hypothetical individuals on the other side, it focuses on minimizing something called delta. And delta is the additive shift applied independently to each of the features that would project Edward to the other side. You might ask, well, what is it giving us in this new reformulation? And that is the additional constraints where delta has to be feasible. Because the actions that will be performed in a world governed by a set of constraints. For instance, a bank can't tell an individual to reduce their age to then come and get a loan. Or for the purposes of loan approval, we can't ask someone to change their gender. Or if someone's pursuing a degree, we can't ask them to keep their age constant. So there's a bunch of constraints, and this formulation allows us to capture those constraints directly in the optimization. Okay, so now the question we want to ask is, do these counterfactual-based recourse actions, it's a mouthful, but these deltas, do they translate to optimal and feasible actions to be performed in the real world? And in order to do that, in the last example that I gave, I said that if someone is pursuing a degree, at the same time, some of the other variables will be changing, like their age will be increasing. And so any action to be performed in a world will have consequences. And we need to somehow find a way to model those consequences. To model those, we first review some preliminaries about what causality is. So we adopt the framework called the SCM, or the Structural Causal Model framework of Pearl. He's also a Turing Award winner, where a system is defined as a combination of S and P of U. S is a set of structural equations which determine the value of each of the variables in our system XR as a function of their parents, as well as some background or exogenous variables U of R. And we also have a distribution over the background variables. Let's maybe add a bit more intuition. What does this mean? This means that we want to model a system consisting of, let's say, 3 variables, X1, X2, and X3 within our green cloud. And the green cloud represents the border of our system, the border of understanding what we want to model. And then there's also some additional background variables, exogenous variables, what latent factors, whatever you want to call them, U1, U2, and U3, things outside the system that we don't immediately care about. Now, typically in the causal inference literature, or maybe if you want to take one thing away from this seminar, is that causality is always a game of assumptions. And whatever inference we make breaks apart once those assumptions no longer hold. Very common assumptions within the causal framework is that we assume that the representation of the world can be captured as a graphical model, in this case, a directed graphical model known as a DAG, and that also all of the U1, U2, and U3s that you see in the figure up there are mutually independent. And this is also known as causal sufficiency. Now, for the causality enthusiasts, I remind that when you are operating in the causal framework and with objects such as SCMs, you are entailed 3 types of distributions: observational distributions, interventional distributions, and counterfactual distribution. Just for you to get a bit of intuition, an observational statement could be something like, what % of the population gets headaches after standing under the sun for too long? An interventional distribution would say, what would happen if this population were to splash water on their face? So you're actually performing an action, you're changing the distribution, intervening somehow, and trying to figure out how that distribution changes. And counterfactual would say, well, these people we see here stood under the sun for too long. Had they splashed water, what would have happened? Because you've already observed something, but now you're going back, performing hypothetical actions. Importantly, these 3 questions are different in nature. And how Pearl calls them is that they correspond to different layers of a ladder of causation as different models of thinking. In the first case, you're observing. In the second case, you're acting. And in the third case, you're imagining something about a world that did not happen, but could have or would have happened under some situation. This is how Pearl pitches it. My advisor, Bernard, and some others also formalized this a bit more and said that in the statistical case, that when we have a distribution, we have just one distribution and we're only observing things about the world. We're not touching it. We're not acting it. We're not imagining differences. But once we have an SCM, we can actually have this mathematical object which gives us all of the different types of observational, interventional, and counterfactual distributions in one. So they say it's a compact and parsimonious mathematical object of representing anything about the observed world and anything about imagined worlds. Okay, so why are we talking about this? Again, we're reviewing the preliminaries of causality because what we're trying to do is we're trying to evaluate whether counterfactual-based recourse actions actually result to actions that someone can perform in the world. And that aligns very nicely with counterfactual distributions. Yes?
Are these subsets of each for the of
Yes. So strictly speaking, if you have interventional assumptions for you to make interventional inferences, you can also do observation, but you cannot skip up. At every level, you need to make additional assumptions, and it becomes increasingly harder to actually evaluate statements such as that. Yes. So in this case, it is assumed that you have 3 variables in your system. And if you look at the one up there, there's a hammer. The hammer corresponds to an intervention. You're not performing intervention, you're just looking at the world and trying to model what the distribution looks like. But if you do have an SCM, you not only have this observational distribution, but it also entails all the other types of interventional distributions. But having an SCM is hard. And I'll come back to this multiple times. It's very difficult to actually have an SCM.
So the more comprehensive the intervention space, the less counterfactual things you can consider, right?
because the counterfactual is about, oh, what if instead we have done Y instead of X? But then if when we do interventions, we consider Y and X together, then Y will not be a counterfactual anymore, right?
So maybe let me give an example to build that. So Pearl, in his book, he says, I'm driving down this street and I'm going to say, what happens if I drive down this street instead of that one? If I take the highway instead of the boulevard, right? That's only an intervention. It's now, time is now. That's an interventional query. A counterfactual query says, I've arrived home and I took the highway. What would have happened if I had instead taken the boulevard? I know what happened that I took the highway. For example, it was raining. Whatever path I took would have been super lengthy. But maybe there was a difference. So there's the additional observation or evidence that you have about the world in the counterfactual. There's a question here. Johnny?
To which extent this is different from standard Bayesian network, on top of which to do some
Well, Pearl is the inventor of graphical models. Causality, in my opinion, he can disagree, of course, comes in when you have the additional machinery to actually ask and solve questions like this based on, all of this is based on the Bayesian graphical models. But causality comes in when you assume that the edges actually correspond to some cause and effect in the world. Now, whether that's actually true, whether that aligns, I think that's more of a philosophical question than a computer science question. But from a computer science side, it's a Bayesian probabilistic model with additional machinery to actually infer and answer queries. We have some heavyweights in the audience, so everyone else can also feel comfortable to ask, by the way.
Can I try one too?
Yes.
I'm a lightweight, but I'll try it anyway. So we're trying to answer the question of if I make this recommendation, is it practical? But I feel like what you're describing here is more about figuring out which recommendations to make, right? Like, oh, if Edward had $100,000 income, would I have given him the loan? What would have happened then?
Yes.
But it doesn't really address the question you were trying to get to of, is it realistic for Edward to raise his income to $100,000?
Yes. So I probably misled you there because that's not the main question. We're not trying to see whether it's actually feasible for Edward to come to Qatar, right? That's not the question. That's a question for him. And we probably can't even do so far with modeling that. There's a cost function and he has to tell us how to make that cost function.
Right.
But what we're trying to see is we're trying to evaluate and optimize over various hypothetical scenarios and see which one under his given cost function would give us the smallest cost. But we need to be able to evaluate each of those independent queries, and those queries are counterfactual queries, and hence we need causality.
So is the cost function related to the original decision, or is the cost function something unique to the individual? Do you get
unique to the individual?
Okay, so Edward would provide his own cost function?
Supposedly.
Okay.
And I know that's a tall order, but
sure,
we can't really do anything about it technically.
So in a sense, we're taking what do I want to call it? We're taking the hard part and we're shoving it into the cost function and saying, this comes from somewhere, but if we had it, we could do X, Y, and Z.
I mean, you could take that hard part and average over the cost of different individuals within a population, but it just won't be for Edward. It'd be for average. And we'll see an example of when we can't even evaluate counterfactual queries because it's really hard, because we have too many assumptions, then you need to take average over different individuals. Sure. But we'll see that in a few slides.
Okay, thanks.
Okay, so again, the point of all this is to first see how existing literature, which gave us the deltas, do they actually give us actionable recommendations? So let's go back to the example. Let's look at Edward here, and let's add some numbers just from the initial case study. Edward has a salary of $75,000. He has a savings of $25,000. The bank uses some arbitrary decision boundary. In this case, it's the sign of x1 plus 5x2 minus some threshold. And additionally, importantly, in the world that Edward will be performing his actions, there's some causal assumptions. And that assumption in this example is that people who are seeking to buy a home will be saving 30% of their salary towards their bank balance so that they can actually have the down payment for a home. That's captured there. X2 is equal 3/10 of X1 plus some noise variable. And it's represented, it could be represented by the graph on the right. Okay, so existing methods based on Wachter et al. And Hossein et al. And all these folks would give us these two recommendations, delta and delta star. In the first case, it says increase your salary by 25,000 relative to what you have. That's a 33% increase. Ask for a raise. The second one says increase your savings by 5,000. Maybe go borrow from friends or family or whatever. That's a 20% relative increase to what he had saved before. And so the second one is a relatively less effort, and so it's optimal, and therefore the optimal counterfactual explanation, or XCFE star, would put Edward at this point here. However, these methods have failed to take causality into account. And if you think just a little bit, you can see that there is an additional point, the blue star here, that says that if you only increase your salary by 14% instead of the 33%, then over the time that you're actually making these contributions to your savings, you will have additional savings as well, and together they will push you to the other side of the boundary. Importantly, though, what this is recommending is only a 14% increase in relative effort compared to the existing methods. Okay, in this example, there was a positive causal relation between x1 and x2. It was plus 3/10. And therefore, what we saw was the case where the recommendations were suboptimal. However, the flip side of this is that there's a negative causal relation between these variables, as is the case with the example here. So this is an individual who is farming on a rice paddy, and there's a company that's thinking about the optimal placement of that rice paddy. On average, we know that every 100-meter increase in elevation results in, let's say, 1 degree decrease in temperature, and that's a negative causal relationship. And if you're optimizing over the placement of a paddy without considering the causal relations there, you might end up giving a delta recommendation that doesn't even result in you getting the optimal or the desired output. So not only is the first part of the question answered to say that no, we do not get optimal answers, but they might even give recommendations that are completely ridiculous and don't result in anything useful. To answer the second part about feasibility, we have to ask what it means to actually perform an action. So actions in a world, especially those that we model with structural causal models, can be represented as interventions, that notation of do whatever, that means just perform an intervention on one variable, interventions in a world. And the question then becomes, well, which variables, the ones that we see there, which of those variables are the ones that we're actually intervening upon? And we have two options. Given, again, recall that we're given this delta star from existing methods. Given this delta star, we can either intervene on all of our variables, so all of I in the set that goes up to D, or we can only intervene on those in which the delta I star is non-zero. And each of them have their own problem. In the second case, where we only intervene on some of the variables whose delta I star value is non-zero, we saw in the previous slide that it could have unforeseen consequences on downstream variables, and so that doesn't work for us. And in the case where we're asked to intervene on everything, that also doesn't work, because of the example that we saw when you tell someone to pursue a degree, but you don't say what to do with their age. You can't hold their age fixed. That's not the world we live in. And so, unfortunately, neither of these work. And we arrive at our main proposition of this work, which is that a counterfactual-based recourse action, so this delta star, from existing methods, guarantee recourse if and only if the set of descendants of the acted upon variable is the empty set. What that means is that we're only intervening on leaf variables. And in a complex system, and the systems that we operate in are typically complex, this is very restrictive to be only intervening on leaf variables. And so, unfortunately, the answer is that counterfactual-based recourse actions from existing methods translate to neither optimal nor feasible actions for recourse. Is it all doom and gloom? Let's hope not. So this is, again, the formulation by Hossein et al. And then the one on the right is a reformulation that we came up with, which instead of focusing on the minimum cost shift, we changed the focus to be on minimum cost interventions. I don't know if it's clear. There's a yellow highlight on the third line. So we're really just replacing the constraint on the left with the one on the right, where what it means, it's this complicated FA, F inverse, but what it really means is just evaluate the counterfactual query under some hypothetical action that's performed, and then minimize the cost over the cost of that action. A couple remarks about this is that although existing methods allow us to work in worlds in which the variables are independent. Unfortunately, that's not the case for most of the problems that we have. And our formulation allows us to extend to arbitrary causal models or causal SCMs of the world. In addition, we called these counterfactual-based recourse action. But unfortunately, we argue that this is a misnomer. And because counterfactual is a term or a terminology from the causal inference literature, it's best that we don't confuse it when we're actually not doing causality. And so our suggested name for them is to use contrastive explanations versus consequential recommendations is what we are offering. I think there was a question maybe by Christos that earlier outside in the hallway, that what is the difference where we are applying our interventions? And the difference really is that existing methods apply them here at the input to the black box, and they assume that features are independent, which we argue is not the case. We can just show with simple examples. But instead, we know that what goes into the black box, what goes into a classifier, is itself the result of some underlying process of nature. And it's best to model that process and actually perform the interventions there when we're giving solutions. Are there questions?
So the representation so far is simple. You assume there is one direct edge between two nodes in the graph, and that's actually what you are trying to enter from. What if you consider multiple hops across the graph? Is that something that you have looked at?
So are you asking whether we can group some of the variables together and see what their effect is?
Then you can do that, or you can go, so if if X3 is dependent on X2 and X2 is dependent on X1, then there is an associative relationship here between X2 and X1.
Right.
Maybe you can group X1 and X2 together, or maybe you can, I don't know.
Yes, I mean, that is not the case that we assume. Generally, when you deal with cycles, it becomes very difficult. Or cycles are otherwise represented by confounding variables in the exogenous variables, which is also assumed to not be the case. We have causal sufficiency, and we assume the direct acyclic graph. So there's no cycles and there's no confounding going on. And this itself is hard. So no, we haven't. Yes.
Yeah, I think in the previous slide there was a proposition. Was that a proposition of the kind that we prove, or good? I suppose
It's the same thing. Yes, same.
All right, good. And so this is something that there's a proof for this, and
yes,
and it's like a complex proof.
It's not too complex. Most of it is really just by contradiction, really. And most of the proof sketch was already in the slides. You can show that if you don't intervene on this, then there's going to be consequences that you can't foresee.
Okay.
Yeah. Okay. So from the first paper, that was very, very difficult to get in because we were suggesting something that was different and people just didn't want to agree. The proposition is that you can only use existing methods if they're suggesting interventions on leaf variables. In follow-up work, which was finally accepted before the first work, what we showed is that ignore all existing literature. What are the conditions under which you can actually give a recommendation to an individual? And it turns out that unless you actually know the true causal model of the world, only if you know the true causal model of the world can you actually expect to solve an optimization problem that gives you the optimal answer or the optimal action to do recourse. And this is an important result because I think throughout the slides and the talk, I've been saying that causality is hard and modeling the real world with causality is harder. And most times we just don't have the true causal model. We don't have the M-star oracle. And so what is the takeaway? The takeaway is that we cannot really expect to guarantee recourse deterministically. Perhaps we can make some assumptions and throw some uncertainty in there and give probabilistic recourse, but we can't do it deterministically. Let's look at what this means. So this is just for intuition, illustrating the summary of the follow-up work. But imagine that, again, this is Edward, that's a decision boundary, and he's operating in the world M star, which is unbeknownst to us. We don't know what M star is. And he performs some action A, which throws him to the other side. Now, because we don't know M star, we can't really get that action. But we can make assumptions about the world. we can maybe say that the world is M1 or M2 or M3, and they all have some similarities. For example, they all have additive noise, specific type of causal models called additive noise models. And so if we make that assumption, then we can go through the steps and actually formulate what the counterfactual distribution would now look like on the other side. And hence we get a green cloud. And then the point would be, well, within this green cloud, how do I find the minimally costly action A under all of those families of models? Yes? Infinite, because we use a Gaussian process. And so actually, we assume an additive noise model, and then supposedly there's an infinite number of additive noise models that we can fit with our Gaussian process, and we can get a closed form distribution for the counterfactual distribution. And then we optimize over that.
Is it possible that this wide range of worlds gives you a much bigger green cloud?
Absolutely. And that green cloud completely depends on the action A itself. It could be super tiny for one action, super large. If you intervene very high up in the tree, everything's going to change underneath. Okay, but sometimes we don't want to assume additive noise model. Sometimes that's too much as well, because additive noise literally says just add a noise to the end of whatever function you have, but maybe you have a more general function. And so unfortunately, in that case, I think there was a question that we no longer can look at Edward alone. If we do not make that level of assumption, remember the causal ladder, we just cannot go to the top ladder, top step of that ladder, period. So we can't evaluate counterfactual queries. But maybe one step down, we can evaluate interventional queries. And interventional queries, like we said, are on some population you want to perform an action. And so this population could be similar individuals to Edward, such as similar software engineers who are 28 years old. And then you try to give an action that works for all of those subpopulations. And this is called, well, subpopulation-based recourse, or it's optimizing over an interventional distribution. Naturally, the higher up in the tree you go, the larger that population is going to be, and the resulting population on the other side. Okay, so just to put everything on the same slide, ignoring the previous literature, we propose one type of deterministic recourse and two types of probabilistic recourse. Each of them have their own set of assumptions, and if those assumptions don't hold, or if a reviewer doesn't agree with your assumptions, then all of it falls apart. Any questions before I move on? Okay, yes. Being linear. That's a good question. If the decision boundary is linear, in some special cases, you can find a closed form, kind of just project the person on the line. But those are very special cases. So in general, it doesn't really matter. And what we show, at least in the second work, is that it could be a random forest, it could be an MLP, whatever it is. It's a black box for our purposes. Okay. So moving ahead, the questions that we answered here were all about Edward. But we said that there's other stakeholders involved as well. And so what remains as partially open questions is, how does one offer recourse that is not only feasible, that is not only optimal, but it's robust, it doesn't violate security or privacy, it's fair across different individuals. If I get a recourse recommendation and you get a recourse recommendation, it shouldn't be biased towards one of us. And that it doesn't enable strategic behavior. If I'm giving a recommendation from someone, they shouldn't be able to come back and try to manipulate my system. So how do you manage all that together? And so these are all, we've made some contributions in the robustness and fairness section, but it's very much an open question. So let's summarize kind of PhD contribution part. In general, counterfactual explanations do not imply consequential recommendations. We need to take causality into account. Recourse can only be guaranteed under perfect causal knowledge, and otherwise we need probabilistic approaches. And naturally, there's a trade-off between how much of assumptions we're willing to make and how individual specific recommendations we can get. And finally, because of the diversity of stakeholder needs, as we saw on the previous slide, most of the solutions are not going to be technical alone, and it's going to require cross-disciplinary expertise of both technical and social scientists. Now, I want to end this part by saying that recourse is important, not just for the loan application example, but for generally any consequential domain in which we are using a machine learning-based system to make any sort of decisions. And hopefully, with the contributions that you saw here, we've made a step towards the first question of the project, which is how does one recover from or overturn poor experiences made via AI? Okay. However, to continue towards trustworthy human-machine collaboration, we need to think about what that collaboration looks like. And collaboration, of course, is built on communication. So how have humans communicated in the past? Of course, we saw the slide here. And I want to re-emphasize that I believe that the next step in this and to solve the questions of the research agenda is to facilitate even more interaction between humans and AI. Specifically for the case of ChatGPT, when it gives you a wrong answer confidently, you should be able to query its answer, challenge its reasoning, and communicate over a substrate which you both understand with meaningful concepts. That word concept we'll get back to. To achieve this goal safely and effectively, it will, of course, be necessary to bring together expertise from across different groups, software engineers, social scientists, cognitive scientists, and computer scientists. And collaboration has many different facets. So specifically, I focus on the intersection of these three subfields of AI, whereby explainable AI aims to answer why questions and promote conversation about a system's predictions. Causal inference, or actually next up is program synthesis, allows for the discovery of models using non-code specifications. And we'll see an example of this and what it means. And finally, causal inference grounds all of these methods in a very nice mathematical framework, which is also commonly used as a model for human cognition. At this intersection, there are 3 or 4 questions that I've presented in my research statement, and we'll see a summary here, which is how can causal inference be used to certify the correctness of a diverse body of explanation methods? How can program synthesis be used to guide the creation of new explaining as programming methods? And how can all 3 of them be used for collaborative concept learning? Okay. So for the first part, we know that explainability is central to the development and deployment of many machine learning models. And it's used as an umbrella tool when we can't certify other features that we want from our models. However, unfortunately, there are many cases where we can't trust the explanation themselves. And so we'll see a couple examples here. So one common type of explainable AI method is called saliency maps. As you see here, for example, there's an original image, and then each of the columns shows one type of saliency map generator, which shows us where in the image has the model focused to arrive at a particular decision. What's immediately obvious on the left-hand side, and this is from a paper called Sanity Checks for Saliency Maps, arguing that saliency maps are not as sane as we hope. What's immediately obvious from here is that each of these explanations are giving slightly different focus to different parts of the image. And so that should make us wonder which one is actually more correct. Additionally, and perhaps more worryingly, what this shows is that if we're generating explanation for an MLP, some neural network, and if we start from the end of the neural network and slowly randomize the weights of that network, so we're completely by the end getting a bogus, just the connection of weights, it turns out that for some of the explanations, the explanation doesn't change at all. Look at the 4th row, for example. If you completely randomize the network, the explanation remains the same. And so that begs the question, what are we actually explaining? Because supposedly we've trained a model, and we want to explain something about that, but that's not what's happening here. The explanation is remaining the same. Of course, this phenomenon isn't just unique to explanations. The literature on underspecification says that we could have multiple models that have identical performance in one thing that we care about, like predictive performance, but have completely different performance on some other metric. One be fair and one be completely unfair. And how do we select between these, and what does that mean for downstream tasks? Okay, and so just to give a high level kind of what this research agenda would be, we start off by showing, again, how explanations are generated, starting from hyperparameter selection. Through the training procedure, we get a model, and then using a sample, we predict or infer what the value of that label should be, and then we get an explanation. So using the tools from causality, we could say, if I had changed the optimizer from value A to value B, how would that affect everything else downstream? So similar to all the other counterfactual queries that we had. And throughout this process, this is preliminary work that we're doing, but we're trying to evaluate the effect of the hyperparameters on the prediction and the explanation to better understand the relation there. Yeah. The back of the slide, is that? Yeah.
So why does the explanation matter if the potential output of the algorithm is good? I might be missing what you're trying to say here, but looking at the first one,
sure.
Why do I care about what the algorithm is focusing on in terms of the perception of the image, so we can classify what the image is?
Let me ask you a question. So a student comes up to you, hands in an assignment. The assignment is correct. You don't know how they arrived at that. You're going to ask for some explanation as to show me step by step what happened. You probably wouldn't accept them just giving you the correct answer, but you want to make sure it's correct for the right reasons. There's literally a paper called Right for the Right Reasons. And even if the prediction is correct, we might still expect some explanation.
Okay, I'll answer that. The student case, I care.
Listen up.
Verifying that the learning occurred.
Yes.
That does not necessarily reflect the correctness of the answer.
Sure.
One facet of that.
Yes.
In the AI algorithm, I don't care. I care only about the correctness of that in a particular algorithm.
Sure.
I don't see the analogy.
Yes. Well, you broke down the analogy. Very nice. Yes. In this case, though, there are the correctness under the situations where the prediction is actually correct might help us understand the cases where it's not correct. So it would guide if you have robust explanations in the sense that they're not basing off some random feature somewhere. There's literally case studies showing, like in the medical domain, you have a predictor that's very good, but then it turns out for some reason, using saliency maps actually, which we're arguing are not entirely sane, but using saliency map, it turns out that it's not even looking at the MRI image. It's looking at some digit in the top right corner of that. Right.
Error, it tells me based on this image the correct output of what I'm asking.
Because I think what we're talking past each other is that you're focusing on one instance. I'm focusing on the entire population. It's, I think, unreasonable to expect the model to work completely within domain for everyone, unbiasedly, and then also extend out of domain. It's going to fail at some point. And we want to understand where that is and why that starts to fail. The example I gave was exactly for a fairness, because it looked at some demographic and looked at some other demographic, were perfectly for these demographic, but like didn't work for the other ones. And it turns out it was focusing on the wrong thing altogether.
For instance, in medicine, if you talk to medical doctors, they will tell you we need to understand why the algorithm, for instance, is coming up with that diagnosis. What were the things that they
right.
considered to come up with that diagnosis? And to challenge them, the answer is, oh, we can leverage that to do preventive medicine.
Sure.
Like, we can understand what's happening.
Right.
We can maybe start dealing insights and maybe understand how to prevent these kinds of diseases.
Exactly.
But that's the problem. I didn't build the model to answer the second. I built it for the first. Now, if you're trying to use this, so I did for extended use case. That's different. Fairness is a different objective than what I originally built the model for.
Yes.
Well, then rebuild them. But I guess what you're trying to do is, I guess, based on what I understood, is if I already know how we got to answering the initial problem, I might be able to leverage that for a different context.
Sure, absolutely. I mean, I don't think these two are separate cases. Yes, if we understand how it got here, we might understand how it didn't get somewhere else. But it's not that. So in the case of the fairness that you said, yes, we're going to go and now train a model that supposedly is predictive and fair at the same time, but it's still going to fail. In that case, what do? I use saliency maps, and then I'm like, oh, it's actually looking at whatever, like, cow classification. Cows are typically on grass. But if you put a cow on a beach, the classifier will now not predict it well. And it turns out that's not because of the cow. That's because you had a poor classifier. It was a grass detector rather than a cow detector. And these are literally deployed models. It's quite shameful to say, but That's where we are. That's why we need explanations. This can go back and forth, yeah. Okay. So anyways, yeah, we try to use causality. This is, again, preliminary work, but we model this system. Supposedly, you can see this as a structural causal model, which we call an explanation generation process, to evaluate how the hyperparameter changes affect everything else in the system and study the relation between explanation and prediction. The preliminary work, which supposedly is answering the second question of the research agenda, says that we typically use explanations to assay the safety, factuality, fairness, and all these other good stuff that we want. But unfortunately, just like the sanity checks for saliency map paper, we have a cautionary tale whereby now with a causally grounded quantitative metric, we show that explanations may still be explaining something other than the prediction. And so even while we're saying explanations are useful in some cases, we are not saying it's a solution for everything, and we should still be doubtful. Okay, let's shift gears a bit, and I know we only have 10 minutes. Hopefully we'll finish. So let's talk about program synthesis a bit. We haven't really defined it, so let's just briefly do that. The world that we live in is full of repeated recursive structure, like the ones we see here. And for example, fractals are abundant in nature, and we have hierarchical components based off of smaller building blocks that make up, things that we deal with in the real world. And in our search for human AI collaborative systems, we want systems that at the very least can detect these patterns and then communicate them with us. One thing to consider is that an AI agent that would be collaborating with us could do things like discovering symbolic equations from physical laws just from looking at data. It could infer the blueprints of a Lego structure just by seeing the final shape. And ultimately, it should be able to communicate with other agents over a shared vocabulary. Now, beyond what this agent looks like, the solution to all of these problems admits a programmatic structure. So you start with something, then you go through, you have an if statement and the for loop, and all this. It looks like a program can be used to solve all this. So what is a program? A program, in its bare definition, is syntactically correct sequences of tokens and symbols in a domain that semantically achieves some desired functionality. For example, this is code snippet in Python. It's called insert sorted. You have an X float value, and you want to insert it in an already sorted list. And there's comments, and there's different processes that go through where the input arguments go, and then you get a final sorted list. Now, this, of course, is written in Python, and therefore the language that is used is Python. And what we have is we define within our program something called a domain-specific language, the language of the domain in which the programs are written. Now, domain-specific languages are comprised of two things: primitives and grammars. And I'd like to think about these as puzzle pieces. So primitives are each of the puzzle pieces, like you have if and while and return and all these. And grammar is the way that you combine these puzzle pieces together to get a final program. Now, so how does one find a program automatically? This is done through a process called program synthesis, which is the task of automatically finding a program given a particular language. And importantly, the language is supposedly satisfying some user intent. Let's look at an example. So this is a success story from 2013. This feature is shipped in all of Excel worldwide, and it's called flash fill. And what it does is it takes the column A of data, which has a bunch of information in it, and by only specifying a couple of examples of what you want the target to look like, your intent, FlashFill is automatically able to complete the entire column for you. You can try it out. It's on your laptop. I'm not lying. And importantly, what this enables us to do is, this is sed notation from Linux, for those of you who know. It allows us to go from coding to specification, meaning that now we can start to tell machines. And program synthesis is not a new field. It's a very old field in AI. But with the new methods, it's able to actually do things at scale. But we're able to go from coding to specification. And this means that anybody, not just those who know how to write Python, can now start to communicate via their intent and get some functionality out of the system. Generally, the approach is that we define our DSL, we tell what language we want it to write it in, We, of course, specify our intent. Could be logic constraints. It could be input-output examples. It could be whatever you want. And then we search for the algorithm does a big search in a very, very large space. A couple of concrete examples in this is the application of symbolic regression. So symbolic regression says, if I have an underlying data like this, and I sample some points from this data, the unseen expression is actually x times sine of x squared, some complicated thing that I just made up. And if I sample points from this distribution, and I also give it a type signature, I say that, okay, x and y are arguments, and z is the output, so the float to float to float, whatever. Then program synthesis can actually, through the process described on the previous slide, actually give us that unseen expression. But of course, we don't need to just deal with floats. We could have an unseen expression, which is a bit more complicated. This is built on the concept of uniqueness and count and all this. And we could have data input-output specifications that look like this, which is like a list of 4 body elements, and then the number 4, because that's the number of unique elements within it. Okay, so, but why are we talking about program synthesis? And the reason is that we want to find programs in a given language that a human can then communicate, that the computer can then communicate to us humans. And those programs are built on top of concepts. And so we recall that when we want to give explanations to individuals, we want to make sure that those explanations can be understood by those individuals. So we need those to be built on mutually understandable concepts within that language. Now, learning concepts from data has a rich history. Arguably, all of representation learning tries to do this. But most recently, within the explanation literature, we have a method called TCAV, which takes in some neural network and then predefines some human concepts such as stripes or whatever other pattern, animals or trees. And then it tries to see, given a particular input image, what is the representation of that image in the embedding space of the neural network? And how does that align with the concepts the human already understands? So there's concepts the human understands and we want the machine to understand them, but then there's the opposite side, concepts the machine learns and we want to teach them to the human. And that's what the program synthesis method called DreamCoder does, which is that it starts from, like we saw on the previous slide, from simple input-output examples and tries to, through the process of abstraction, give us the concepts that maybe you can then present to a human for teaching. Now, unfortunately, both of these methods have their drawbacks. The first method has a drawback whereby you have to know in advance what kind of concepts you're looking for. But we know that we don't know what we don't know. And therefore, we can't really extend our understanding beyond poking at a neural network with our current understanding. The second one, which is a program synthesis system, has a problem of scale. These are very, very large search spaces. And depending on the language that you use and the task you want to do, you're mostly restricted to very toy models. So we're trying to bring these two together. And one way to do this is to potentially use what's hot these days called transformers or large language models. And these allow us to maybe use few demonstrations using very powerful pre-trained models to actually give us the underlying expressions. Okay. I should point out as a disclaimer that these are future works. Nothing is concrete and of course open to suggestions, but this is an initial just sketch of an idea. Now, the problem here is that communication, as I said, is a two-way street. And this would give us concepts that are understandable by a machine, but now you need to teach them to a human. But of course, you want the human to also be able to guide those conceptual representations. And so maybe the first question we should ask is, what is a good concept if we're trying to align these? And there's a few things that come to mind. First, we want the concepts to be short and tractable so that you can actually discover them via existing methods. You want them, the ones discovered by the AI, to align with human concepts. And you want them to also be adaptable so the human can guide those representations. Another thing you want is you want the representations to be robust and invariant in different settings. Let me give you a concrete example. So if you have an object and then you change the lighting condition, that object's shape does not change. And so that's an invariance inherent to that object. So you want to make sure that the concepts you have also follow these sorts of invariances. And if we recall from slides way back, causality gives us models which are parsimonious representations of the world that remain invariant in different settings. And therefore, the final part of the slides looks at how we can maybe use the intersection of all of these fields to try to use program synthesis to learn something called causal probabilistic programs. So at the very top, we saw causal graphical models, we saw SCMs, but that's not the only way to actually try to capture causality in the world. You can also use a program to capture causality. Some people also argue that the programmatic representations are more easy to understand and more easy to then intervene upon. So maybe they might be a superior representation. Don't tell Pearl I said that, but open debate. But importantly, we have to remember that we have this causal ladder, meaning that from purely observational data, if we only look at the static world through fixed demonstrations from the past, we can't really jump to the next level. And this means that in this case, where we have causal probabilistic programs, which in the observational case, we won't be able to recognize the difference between those two, then we need additional assumptions or additional data in terms of the intent used for program synthesis. And so building off the previous slide, we have now, in addition to just observational static data about the world, we need to be able to give experimental data through some interaction between the human and AI in order to maybe guide the transformer to give us a causal probabilistic program as its output. Okay, we're at time, but I only have a couple slides left. Let's go back to the initial story. We said that we want to address these 3 questions. And throughout the slides, we've talked about 3 or 4 different specific projects that could address the questions in the research agenda. With that, I thank you for your time. Happy to take questions. I've either managed to confuse all of you or convince all of you. I'm not sure. Yes.
So maybe at the first part of the talk, we were talking about I remember the equations there. If I understand correctly, the structure of the work is, there is a model out there. I'm trying to find examples where that model fails somehow, and then I introduce a new model. And in that model, I can imagine 2 things. Maybe I can prove some things about that model, or in that model, find algorithms that are doing something. Am I correct in the more or less?
Sure, yes.
All right. So I'm trying to understand what part is the most challenging there. Is it like finding counterexamples for the existing models? Is it introducing the new model that addresses those counterexamples? Is it the work inside a model in terms of proving stuff, or in terms of coming up with algorithms that do stuff in that? So what is the most challenging part in that sequence, if the sequence is correct?
Right. So you're right about the first part. We have the world, the natural world, which we never have access to. And all of machine learning, causality, normal machine, whatever, is trying to come up with approximations to that world. We're never going to be correct. We're never going to have the M star, whatever we do. And this is why they say all models are bad, some are useful. So that's point number 1. So that part is always difficult. We're always trying to reduce that part of the uncertainty. Now, let's assume that we're given a model. Let's assume we have a completely engineered system and we know specifically what the structural equations are. This causes that. Even in that case, there's going to be some noise in the system, even with engineered problems. And so handling that noise and figuring out whether the noises are confounding one another, whether they're independent, that gets to the level of what assumptions we're willing to make. Depending on the assumptions that we're willing to make, like causal sufficiency, which is very common in causal inference, we might have an easier job of actually answering queries such as counterfactual queries or not. But if we're not willing to make those assumptions, then causality is very hard. It might be even untestable, what we're doing. And so I think all of it, to answer your question, all the parts, from the real world to the modeling, and then from actually coming up with the answer to a query given a model. All of that is it.
in medicine, there is the symptom, which is the reflection of what is happening to the patient, and there is the risk impact, which doctors say are the causes for the symptoms that the patient maybe is experiencing at the moment, or will experience actually as they move on. And honestly, you made me think about something, and I want to ask about it. I can't. I feel so much intrigued. If we can figure out why the symptom is happening, which means we can explain to the algorithm why the symptom is happening, and as such, why is that actually, why the patient is getting that particular disease that maps to those symptoms, then maybe we can figure a certain causality path.
Yeah.
And maybe we can learn new things.
Absolutely.
About why diseases are happening, and maybe we can come up with better drugs. Maybe we can come up with better preventive medicine. And that goes back, that goes back actually to this question. Is this a right way of thinking about the problem?
Yes. So I subscribe to the idea that if you have the exact causal model, you don't need anything else. You don't need any other machine learning. You don't need any approximation. You have the model. This is the world. The problem is that's an unrealistic dream. And an entire subfield of causal inference is dedicated to causal discovery, which is exactly what you're saying. How do I actually, just from observations or through maybe some interactions, some experiments, how do I come up with a potential graph that mimics what's actually happening in the world? There's a rich literature on causal discovery, and it's equally very difficult because most of the times we can never, so on one of the slides I showed the two causal graphs with a dashed arrow between them. You actually can't distinguish between these two if you only have observational data. You don't know which direction this points to. Even in the simple case of two variables, elevation and temperature. If you only give that to a model, the best you can do is regress this variable on that or that variable on this. You don't know which caused the other. We know because in our case, we've had scientists went up, oh, it's colder. That's an experiment. That's not an observation. That's just an experiment. And that means we need additional types of data to actually be able to go up that ladder and learn more things about that. And so causal discovery is the field of what level of additional data do I need to arrive at what level of specification of causality in the real world.
Is there a book that you recommend that I read about that?
About causal discovery, there's a paper called Do You Like Dags? Which is, and it's spelled D''YA, Do You Like Dags? I don't know, they were funny at the time. But generally for an intro to SCMs, Pearl has a book which is called A Primer to something causality, and it's freely available on his website, so you can.
Thank you.
Okay, well, thanks for everyone coming.